Somewhere in our galaxy, an object the size of a city outweighs our Sun. Its magnetic field is 100 billion times stronger than Earth's. At 600 miles away, it would pull the electrons out of your atoms before you saw it coming. We are going inside a magnetar. We will watch atoms get crushed into needles. We will see empty space split light in two. We will stand at the edge of where physics stops making sense. If you enjoy the journey, subscribe. It helps more than you know. Brace yourself. We begin. The most violent event in the universe takes about 10 seconds, not 10 minutes, not 10 hours. 10 seconds. That is roughly how long it takes for a star many times bigger than our Sun to completely destroy itself from the inside out. And in those 10 seconds, something survives. Something that should not exist. Something so extreme that the laws of physics we use every day stop working inside it. To understand what a magnetar is, you first have to understand what dies to create one. Picture a star, a massive one, maybe 30 times heavier than our Sun, burning for millions of years in the dark. It runs on nuclear fuel, the same basic idea as a bomb, except controlled, steady, burning outward in all directions. That outward pressure is the only thing holding the star up against its own gravity. Then the fuel runs out. The moment the fuel dies, the pressure dies with it. Gravity, which had been held back for millions of years, wins instantly. The outer layers of the star, material that weighs more than most people can imagine, begins falling inward at a quarter of the speed of light. Everything collapses toward the center at once. What happens in the core during those 10 seconds is one of the most extreme events in the known universe. The collapsing material compresses the center so violently that something remarkable happens to the atoms there. On Earth, an atom has a nucleus in the middle and electrons orbiting around it, with a huge amount of empty space between them. Most of an atom is empty. Under normal conditions, that empty space stays empty. But under the pressure of a collapsing star, that empty space disappears. The electrons get forced directly into the protons inside the nucleus. They merge. Protons and electrons combine into neutrons. The atom essentially collapses into itself. What remains is a sphere of pure neutrons, packed so tightly there is no space left between them at all. The entire core of a star, something that was once the size of a small planet, compresses down to a sphere about 12 miles across. 12 miles. You could drive that distance in about 15 minutes on the highway. That 12-mile sphere now contains more mass than our entire Sun. Meanwhile, the outer layers of the star, still falling inward, slam into that suddenly rigid neutron core and bounce back outward in a catastrophic explosion. That explosion is the supernova, the blinding flash that can outshine an entire galaxy for weeks. But the core survives. That core is now a neutron star, incredibly dense, incredibly hot, spinning fast, because when something that large collapses into something that small, it spins up the same way a figure skater pulls in their arms and spins faster. Some of these newborn neutron stars spin dozens of times per second. Most neutron stars settle down into a long, quiet existence, slowly cooling over millions of years. But some of them, in the first 10 seconds of their new life, experience something different. The conditions inside the collapsing core line up in a very specific way. The temperature and the spin rate hit a precise combination. A powerful churning motion starts inside the still-forming star, and that churning does something extraordinary to the magnetic field. Most neutron stars have a strong magnetic field. These newborns end up with something unimaginably more powerful, something that does not just bend metal or deflect compass needles, something that breaks atoms. What triggers that transformation inside the newborn core is the story of the next chapter, and it happens faster than you can blink. 10 seconds. That is the entire window. During the first 10 seconds after a neutron star forms, a decision gets made. The star either becomes an ordinary neutron star, a remarkable object on its own, or it becomes a magnetar, the most magnetically powerful object in the known universe. The difference between those two outcomes comes down to what happens inside the core during those first moments. Scientists call the process a dynamo. You have seen a dynamo before, even if you did not know the name. A dynamo is what powers a bicycle light when you pedal. Spinning motion gets converted into electrical energy, which generates a magnetic field. The Earth itself runs on a dynamo. Its liquid iron outer core flows in patterns driven by heat and rotation, and those flows generate our planet's magnetic field. Inside a newborn neutron star, a dynamo can also form, but the scale and speed are completely different from anything on Earth. The newly formed neutron star is still incredibly hot enough that powerful currents of material churn through the interior. At the same time, the star is spinning rapidly, sometimes dozens of times per second. When those two conditions, the churning heat and the rapid spin, align in just the right way, they work together like two gears meshing. The churning interior begins moving in organized, powerful loops. Those loops drive electrical currents. Those currents generate a magnetic field. And because the star is spinning so fast and the currents are so powerful, the magnetic field amplifies itself in a feedback loop that grows stronger every fraction of a second. In 10 seconds, the magnetic field grows by a factor of 1,000. Think about what that means. An ordinary neutron star already has a magnetic field billions of times stronger than Earth's. A magnetar's field reaches 100 billion Teslas. Earth's magnetic field measures about 500 thousandths of a single Tesla. The difference is so large that numbers stop being useful for picturing it. Here is a better way to see it. If you could somehow replace the moon with a magnetar, its magnetic field would reach Earth instantly. Every credit card on the planet would be wiped clean. Every hard drive, every computer memory chip, every magnetic strip on every subway ticket would be erased simultaneously. And that would happen from 239,000 miles away. The magnetar would still be sitting there, doing essentially nothing. After those first 10 seconds, the window closes, the internal temperature drops, the churning slows. The dynamo freezes into place, locked inside a star that has now solidified into its final form. Whatever magnetic field the star built in those 10 seconds is the field it keeps, and scientists still cannot fully explain what tips the balance. Some models suggest the original star needs to be spinning at a very specific rate before it collapses. Others suggest the temperature gradient inside the core has to hit a precise value. The truth is that researchers have identified the conditions needed, but recreating or predicting which stars will produce magnetars remains an open problem. What we do know is that the result is a locked, permanent magnetic field of almost unimaginable strength, sealed inside a star that has now begun to cool and harden from the outside in. The outside of a magnetar is nothing like the inside. The surface is solid, rigid, harder than anything that exists on Earth. And understanding what that surface is made of and why it holds together at all is stranger than it first sounds. The dynamo inside a forming magnetar runs for 10 seconds and leaves a permanent mark on the universe. That sounds like a short window, and it is, but inside that 10-second burst, the physics happening inside the collapsing star are more violent than anything a laboratory on Earth could ever recreate. The churning is driven by heat differences so extreme that currents of neutron-rich material move faster than hurricanes, faster than any fluid on Earth has ever flowed, and the rotation driving those currents is measured in dozens of full spins per second. To picture the dynamo itself, think of a pot of water heating on a stove. The hot water at the bottom rises, the cool water at the top sinks. That circular motion is called convection, and it is the engine behind Earth's own magnetic field, just on a much slower, gentler scale. Inside a newly born neutron star, the same convection happens, except the temperature difference driving it is hundreds of billions of degrees, and the entire cycle runs in fractions of a second. As the churning material moves, it carries electrical charge with it. Moving charge generates a magnetic field, and because the star is spinning so fast, the generated field wraps around itself, reinforcing and amplifying with every rotation. Scientists call this process a convection-driven dynamo, and the amplification it produces is what separates magnetars from every other object in the universe. The field grows by a factor of 1,000 in those 10 seconds. 1,000 times stronger than the already powerful field a normal neutron star would have, and then the window closes. The temperature drops just enough. The convection slows. The dynamo freezes. The field is locked in, permanent, encoded into the structure of the star itself. Permanent for now. We will come back to that. What is fascinating is how much scientists are still working out about the details. The exact temperature a forming neutron star needs to reach for the dynamo to ignite is still debated. The exact rotation rate needed is still a target of active research. Scientists have found several neutron stars that should have become magnetars by the models but did not, which means the models are still incomplete. One of the most striking things about this 10-second event is that it cannot be reversed or adjusted. Whatever field gets locked in during those first seconds defines everything about the magnetar's future. The starquakes it will experience thousands of years later, the gamma-ray bursts it will fire across the galaxy, the way it will eventually decay and quiet down. All of it is determined in 10 seconds, at the moment of birth. That level of locked-in consequence is unusual even by cosmic standards. The other striking thing is what the field does not do during those 10 seconds. It does not settle evenly across the star like a smooth blanket. Scientists believe the field locks in with uneven patches, stronger in some regions than others, twisted and braided through the interior like a cable under tension. That tension matters enormously. Because the outer shell of the magnetar is solid and rigid, and the field running through it is under constant stress, the star is always at war with itself. The field wants to move. The crust refuses to move. That conflict builds over centuries. And when it finally breaks, the result is one of the most powerful single events the universe produces. But before we get there, the structure of the star itself deserves a closer look, starting with just how small and how impossibly heavy this thing actually is. Stand in the middle of a city, any city. Look from one edge of downtown to the other. For most cities, that distance is somewhere between 8 and 15 miles. A magnetar fits inside that. The entire object, the most magnetically powerful thing in the known universe, the thing that can kill you from 600 miles away, is 12 miles across. You could theoretically drive from one side to the other in the time it takes to watch a TV episode. And yet it contains more mass than our Sun, a star so large that 1,300,000 Earths could fit inside it. That combination, city-sized but heavier than the Sun, produces numbers that feel wrong, and the feeling is correct because they defy everyday intuition in almost every way. Start with density. A single teaspoon of magnetar material would weigh roughly 1 billion tons. Picture a teaspoon of sugar, the kind you stir into coffee. Now picture 1 billion tons. That is about the combined weight of 5,000 fully loaded aircraft carriers sitting in a spoon. The reason is packing. On Earth, atoms have a nucleus at the center and electrons floating at a distance, with mostly empty space between them. A magnetar eliminates that empty space entirely. Every neutron is pressed directly against the next one. There is no room left. The material has been compacted to the maximum density that ordinary matter allows. Ordinary matter, at least. What happens at the very center may push past that limit. Scientists suspect the pressure there might be high enough to break down the neutrons themselves into something more fundamental. But we will get to that later. The extreme density also has a direct effect on gravity at the surface. The surface gravity of a magnetar is roughly 200 billion times stronger than Earth's gravity. On Earth, if you drop a ball, it accelerates downward at about 32 feet per second. On a magnetar surface, that same ball would accelerate downward at 6 trillion feet per second. A marshmallow dropped from 1 inch above the surface would hit with the energy of a nuclear weapon. Anything that falls onto a magnetar gets compressed and destroyed almost instantly. The gravity also warps the space immediately around the star in ways that become measurable. Light passing close to the surface gets bent significantly. Time near the surface runs measurably slower than time further away, a real effect predicted by general relativity and confirmed in neutron star observations. The size is also deceptive in another way. Because the star is so small and so dense, it spins extraordinarily fast. The same physics that make a figure skater spin faster when they pull in their arms apply here. A massive star that was once millions of miles across collapses to 12 miles across, and the spin rate explodes. Some magnetars rotate several times per second. At the equator of a spinning magnetar, the surface moves at a significant fraction of the speed of light. Something 12 miles wide, heavier than the sun, spinning multiple times per second, wrapped in a magnetic field that rewrites physics, and covered in a layer of solid iron harder than anything humans have ever produced. That outer crust is the first barrier between us and the madness inside, and it is strange in its own right. The surface of a magnetar is solid. That surprises most people. Stars are made of gas and plasma, hot swirling material with no fixed surface at all. But a magnetar has crossed into a completely different state of matter. Its outer shell is a rigid, crystalline layer made primarily of iron nuclei, locked into a tight, organized grid. Think of it like a metal lattice. The nuclei sit at fixed positions, and electrons flow freely through the gaps between them. The same basic structure as a metal conductor on Earth. A copper wire works the same way at room temperature, with electrons drifting through a lattice of copper atoms. The magnetar crust works on the same principle, just under conditions that would vaporize copper instantly. The pressure at the surface is already millions of times higher than anything at the center of the Earth. The temperature, even after thousands of years of cooling, still reaches millions of degrees. And yet the crust remains solid because the gravity and pressure pressing down on it are so extreme that the atoms have no choice but to stay locked in place. The result is a material with mechanical strength that dwarfs anything humans have manufactured. Steel, the strongest common structural material we use, has a breaking stress of roughly 100,000 pounds per square inch. The magnetar crust, according to calculations by researchers, has a breaking stress roughly 10 billion times higher than that. 10 billion times harder than steel. For comparison, imagine pressing your finger against a soap bubble. The force you would need to break a soap bubble relative to the force needed to crack the magnetar crust is roughly the same ratio as a gentle poke compared to detonating every nuclear weapon on Earth simultaneously. The crust is also thin by stellar standards, somewhere between half a mile and a mile deep. Beneath it, the pressure climbs into a regime where the rigid lattice structure cannot survive, and matter transitions into something fluid and deeply strange. But inside that thin crust, something else is happening that matters enormously. The freely flowing electrons, the same ones that give the crust its metallic properties, are doing more than just conducting electricity. They are carrying current, and current generates a magnetic field. The crust is, in a sense, an enormous battery and electromagnet wrapped into one. The electrons flowing through the iron lattice help sustain the massive magnetic field that defines the entire star. Remove the crust and the field begins to decay. Crack the crust and the field lurches. Both events have catastrophic consequences. The crust also stores enormous mechanical stress. The magnetic field running through it is constantly trying to shift and reorient. The rigid iron lattice resists that motion. Over centuries, the tension between the shifting field and the locked crust builds the same way stress builds along a fault line before an earthquake. When the crust finally breaks, the energy released dwarfs the most powerful events humans have ever witnessed. But beneath the crust, before any of that violence happens, there is a layer of matter that behaves in a way that has no comparison anywhere on Earth. A layer where friction disappears entirely, where fluids flow without any resistance at all, where physics enters territory so far from everyday experience that describing it requires abandoning most of the language we normally use for motion. The layer beneath the crust flows without stopping, without slowing, and without ever losing energy. The Magnetar crust is 10 billion times harder than steel. That number is technically accurate, but it is genuinely useless on its own. Numbers that large stop connecting to anything real. So let's try a different angle. Scientists who study material strength talk about something called elastic modulus, which is basically a measure of how much force you need to deform a material. Diamond, the hardest natural substance on Earth, has an elastic modulus of around 1,000 gigapascals. A gigapascal is already an enormous unit of pressure, roughly 10,000 times the pressure at sea level. Diamond resists deformation better than almost anything on Earth. The Magnetar crust has an elastic modulus estimated around 30 million gigapascals, 30,000 times stiffer than diamond. There is no material on Earth to compare this to. The periodic table runs out. The strongest materials humans have ever engineered, including carbon nanotube composites and metallic glass alloys, do not even approach the Magnetar crust. They would behave like soft foam in comparison. The reason is layered pressure. The gravity pushing down on the crust is 200 billion times Earth's surface gravity. The magnetic field pressing in from above and below squeezes the lattice further. The temperature, while still millions of degrees, is low enough relative to the pressure that the material stays crystalline instead of melting back into plasma. All three forces working together produce a lattice of iron nuclei so tightly compressed and so mechanically locked that cracking it requires a force that would seem absurd in any other context. A research team calculated what it would take to fracture a piece of Magnetar crust the size of a sugar cube under these conditions. The energy required is comparable to the total energy output of the Sun over several months for a sugar cube, and yet the crust does crack. Eventually. Always. The magnetic field is the culprit. The field runs through the crust like cables run through a suspension bridge, under constant tension. Over time, the field slowly shifts and pulls. The cables tighten. The bridge resists. Then, at some unpredictable moment, the stress exceeds even the extraordinary strength of the crust material, and a fracture opens. That fracture is microscopic. We are talking about a crack that might be smaller than the width of a human hair, measured across a star. But the densities and pressures involved mean that a microscopic crack on a magnetar is not a small event. The crack displaces material that weighs billions of tons per cubic inch. The energy that was locked in the strained lattice releases all at once. The result tears across the galaxy as one of the most powerful bursts of radiation ever measured. But there is something else the extreme hardness of the crust does that is less dramatic but equally strange. It traps the matter beneath it. The material under the crust is under so much pressure that it behaves in ways the surface world never sees. The pressure is building from the crust downward, each layer adding weight, until deep enough that atoms themselves start to lose their identity. The transition layer between the rigid crust and the fluid interior is a region where familiar matter starts to break down. Heavy nuclei begin absorbing free neutrons. Atoms grow heavier and more unusual with each passing foot of depth. Eventually, the nuclei become so overloaded with neutrons that they dissolve entirely, releasing their neutrons into the surrounding material. Past that point, there is no crust, there are no atoms. There is only the interior, and the interior behaves unlike anything on Earth. Below the crust, the neutrons flow. They do not slow down. They do not stop. They carry no friction. They move through the interior of the magnetar in organized currents, and those currents have been running completely uninterrupted since the moment the star formed. This state is called a superfluid. On Earth, fluids always slow down eventually. Pour water down a pipe and friction between the water and the pipe walls gradually bleeds energy away. Swirl coffee in a mug and it spirals slower and slower until it stops. Every fluid on Earth eventually comes to rest, because every fluid on Earth experiences friction. A superfluid experiences zero friction, mathematically, literally zero. Helium-4, a specific form of the element helium, becomes a superfluid when cooled to within a few degrees of absolute zero, the coldest temperature physically possible. Scientists first observed this in the 1930s and struggled to explain what they were seeing. When cooled far enough, the helium climbed up the walls of its container on its own. It flowed through gaps too small for any normal liquid to pass through. It refused to stop spinning. The behavior seemed to break the rules. The neutrons inside a magnetar are a superfluid, but at the opposite extreme of temperature. Instead of being cooled into the superfluid state, they are compressed into it. The pressure inside the magnetar is so extreme that the neutrons enter a quantum state where friction becomes impossible. They flow with no resistance, no drag, no energy loss. That frictionless flow has a real consequence for the magnetic field. The neutrons are electrically neutral, so they do not directly generate magnetism. But protons inside the core are charged, and they move with the neutron superfluid. Moving protons generate magnetic field lines, and because the protons move without friction, those field lines get locked into the flow pattern permanently. Any change to the neutron current changes the field. Any change to the field changes the current. They are linked. This coupling means that when something disturbs the interior of the magnetar, for instance when the crust cracks in a starquake, the shock wave does not just shake the crust, it ripples into the superfluid interior and disturbs the flow. The superfluid responds because it has no way to absorb the energy through friction. The disturbance travels through the interior and returns to the crust altered. Scientists believe this interaction between the rigid crust and the frictionless interior amplifies the violence of starquakes far beyond what the crust crack alone would produce. The interior becomes a resonance chamber for destruction. And there is something inside the superfluid zone that scientists have been debating for decades. The protons flowing alongside the neutrons may be doing something even stranger than superfluidity. Under these conditions, protons can pair up quantum mechanically and enter a state where they conduct electricity with literally zero resistance. That state is called superconductivity, and in a magnetar, it may have direct control over how the enormous magnetic field behaves over time. Whether the core of a magnetar is truly superconducting remains an open question. The math suggests it is possible. The observations have not yet confirmed it definitively. But something far stranger may be happening even deeper. In the innermost region of the core, where the neutrons themselves may no longer exist as neutrons at all. The deeper you go into a magnetar, the less the material inside looks like anything physicists expected. At the surface, the crust is made of iron nuclei in a rigid lattice, recognizable to any chemist. A foot below the surface, those iron nuclei are getting heavier and more exotic, absorbing stray neutrons and growing unstable. A few miles deeper, the nuclei dissolve entirely, releasing their neutrons into a sea of free particles. By the time you reach the interior, there are no atoms at all. But the story does not stop there. The outer interior of a magnetar is dominated by free neutrons, protons and electrons moving in that frictionless superfluid state. The particles are still discrete. They still have identity. A neutron is a neutron. A proton is a proton. They are distinguishable things. Deeper still, something changes. The pressure rising as you descend through a magnetar does not plateau. Each layer of material above adds its weight to the layer below. By the time you reach the boundary between the outer core and the inner core, The pressure has climbed so high that the behavior of matter enters a regime that no experiment on Earth has ever directly tested. At these depths, scientists suspect that the orderly superfluid of neutrons may give way to something stranger. Some models predict that the neutrons in the deep core get packed so tightly that their internal structure begins to matter. A neutron is itself made of smaller pieces called quarks. Under normal conditions, quarks are permanently confined inside their parent particles. A neutron holds its quarks, a proton holds its quarks. The quarks never get out. But under the pressure at the center of a magnetar, some scientists believe that confinement fails. The pressure is so extreme that the boundaries between individual neutrons dissolve. The quarks stop belonging to specific particles. They drift freely through the material shared across the entire interior, the way electrons in a metal are shared across the entire lattice. The result is called quark matter, and its properties are almost entirely theoretical, because no instrument on Earth can recreate the pressures needed to produce it. Quark matter, if it exists in magnetar cores, would behave in ways completely unlike ordinary nuclear matter. It might be a perfect conductor. It might carry entirely different magnetic properties. It might support exotic particles that have been predicted mathematically, but never observed. Some theorists propose that strange quarks, a type of quark heavier than those found in ordinary protons and neutrons, could appear in this material and change its properties in ways scientists are still working to understand. The existence of quark matter inside magnetars is genuinely uncertain. It is a serious scientific hypothesis, supported by theoretical physics, but direct confirmation requires observations that are still at the edge of what current technology allows. What makes the uncertainty exciting is what it implies. If quark matter exists inside magnetars, then the most extreme objects in the universe are hosting a form of matter that has never been directly seen, studied, or held in any laboratory on Earth. The inner core of a magnetar may contain material that falls outside every model of chemistry and particle physics built on ordinary observation. And outside the star, surrounding the surface, the magnetic field is doing something to normal matter that is easier to see and just as unsettling. It is changing the shape of atoms. An atom is round. That fact is so basic that it almost does not need saying. The electron cloud that surrounds an atomic nucleus spreads outward in all directions equally, forming a sphere. That sphere is tiny, far too small to see, but it is the foundation of chemistry. Two atoms form a bond because their spherical electron clouds overlap. The shape of the sphere determines how atoms connect, what molecules they can build, and therefore what substances can exist in the universe. Near a magnetar, that sphere gets crushed into a needle. The magnetic field close to the magnetar surface is so powerful that it completely overwhelms the electric forces that normally hold an electron cloud in its spherical shape. On Earth, the electric attraction between a negatively charged electron and a positively charged nucleus keeps the electron orbiting at a more or less equal distance in all directions, producing that sphere. The magnetar's field is stronger than that electric attraction by an enormous margin. The field seizes the electrons and forces them to orbit only along the direction of the field lines, the invisible threads of magnetic force running outward from the star. Instead of orbiting in a sphere, the electrons are confined to a tight cylinder running parallel to the field. The result is an atom stretched into a spindle. A hydrogen atom near a magnetar surface becomes 200 times narrower than its normal diameter. Picture a marble compressed into a strand of hair. The atom still contains the same nucleus and the same electron, but the electron's entire orbit has been squeezed into a column so thin it barely deserves to be called a three-dimensional object. This transformation has an immediate and total consequence for chemistry. Chemistry depends on the shapes of electron clouds. When two atoms approach each other, their clouds interact in predictable ways based on their spherical geometry. Bonds form at specific angles. Molecules take specific shapes. Water is bent at a precise angle. Carbon forms 4 bonds in specific directions. Life, as we know it, depends entirely on these geometrical rules. Near a magnetar, the geometry no longer applies. The electron clouds are cylindrical spindles, aligned to the magnetic field. They cannot form bonds in the normal way. Standard chemical reactions become impossible. The atoms still exist, but they are chemically inert in a way that has no equivalent anywhere else in the universe. Scientists calculate that a hydrogen atom near a magnetar surface has a binding energy roughly 200 times stronger than normal. It takes 200 times more energy to pull the electron away from the nucleus. This makes the atom extremely stable in one sense, resistant to being ionized, but completely dysfunctional from a chemistry standpoint. Oxygen, carbon, and nitrogen, the building blocks of every living thing, would all be similarly deformed. Complex molecules could not exist. DNA, proteins, cell walls, all of it would be impossible to assemble near a magnetar. Any chemistry-based structure approaching the surface would be reduced to a collection of isolated, needle-shaped atoms with no capacity to bond. But the field's effect on matter does not stop at atoms. It extends into something even stranger. The field is powerful enough to affect something that has no atoms at all. It changes the behavior of empty space. Empty space is supposed to be empty. That is the whole point of it. No matter, no energy, no interaction. A photon of light traveling through a perfect vacuum should travel in a straight line at constant speed, unchanged, until it hits something or travels forever. That is the fundamental assumption behind nearly all of physics. Near a magnetar, that assumption breaks down. The magnetic field surrounding a magnetar is powerful enough to affect something physicists call the quantum vacuum. According to quantum physics, empty space is never truly empty. It is filled with pairs of virtual particles that constantly pop into existence and then annihilate each other almost instantly, too fast to directly observe, but real enough to have measurable effects. Under normal conditions, these virtual particles are chaotic, pointing in random directions, and their effects average out to nothing. The magnetar's field changes that. The field aligns the virtual particles. Instead of appearing randomly oriented, the particles snap into alignment with the field lines, like iron filings near a bar magnet. The result is that the quantum vacuum itself becomes structured. It gains a direction. It becomes, in a sense, a physical medium rather than an empty background. When light travels through this structured vacuum, it behaves the way light behaves when it travels through certain crystals on Earth. A mineral called calcite splits a beam of light into 2 separate beams, each one vibrating in a different direction. The crystal does this because its internal structure is not uniform. It has a preferred direction that treats different light orientations differently. The magnetar's structured vacuum does the same thing. A beam of light entering the region near a magnetar gets split into 2 components. Each component travels at a slightly different speed through the structured vacuum. The effect is called vacuum birefringence, and it was predicted by theoretical physics for decades before scientists found direct evidence of it. In 2016, a research team studying a neutron star called RxJ1856.5-3754, a nearby neutron star roughly 400 light-years away, detected polarized light coming from its surface. The polarization was too strong to be explained by the surface alone. The team concluded that the light had been altered by passing through the structured vacuum around the star. The quantum vacuum had physically modified the light. Vacuum birefringence had been confirmed in a real astronomical object for the first time. This matters beyond being a curiosity. It means that the magnetar's field is strong enough to change the behavior of space itself, to turn the background fabric of the universe into a lens, a region of space that contains nothing, no atoms, no gas, no material of any kind, still acts like a physical object capable of bending and splitting light. Most objects in the universe affect the space around them through gravity. A magnetar affects it through electromagnetism as well, pushing into a regime where the two fundamental forces compete to reshape reality. And if the vacuum can split light, the question is what else it can do. Near the surface of a magnetar, where the field reaches its highest intensity, photons do something that has no parallel anywhere in ordinary physics. They break apart, and they fuse together. Light does not normally interact with itself. Two beams of light can cross paths and pass directly through each other, without any effect. Shine a flashlight at a mirror, and the beam coming back passes through the beam going forward, without interference, without any interaction at all. Photons, the particles that make up light, ignore each other completely under ordinary conditions. Near the surface of a magnetar, that rule no longer holds. The field near the surface is so extreme that it pushes the quantum vacuum past the point where photons stay isolated. Two X-ray photons traveling close to the surface can interact directly with the structured vacuum and merge into a single photon with higher energy, or a single high-energy gamma-ray photon can spontaneously split into two lower-energy photons as it passes through the field. These processes are called photon splitting and photon merging, and they represent a regime of physics that does not appear anywhere else in the observable universe. On Earth, making photons interact directly requires particle accelerators running at extreme energies, slamming particles together at nearly the speed of light to produce collisions so violent that the vacuum briefly behaves as it does near a magnetar. The experiments are precise, controlled, and expensive. Near a magnetar, the same physics plays out continuously across the entire surface, driven by the ambient field alone. The consequence for observations is significant. When a magnetar fires a burst of X-rays toward Earth, those X-rays have passed through a zone where photon splitting is common. Lower energy photons get generated from higher energy ones. The spectrum of light we receive is shaped by this process, smearing and redistributing energy in ways that carry information about the field strength near the surface. Scientists use this effect to map the intensity of a magnetar's field from light years away. The shape of the X-ray spectrum, the distribution of energies across the photons we detect, encodes the history of how those photons interacted with the structured vacuum near the surface. It is a kind of fingerprint. The field leaves a signature on the light itself. There is something else happening near the surface that is equally strange and more immediately energetic. The magnetic field is under constant internal stress. It wants to shift and reconfigure, driven by the dynamics of the superfluid interior. The crust resists that shift. The stress builds, and the field responds by heating the surface unevenly. Hotspots appear. X-rays pour off these hotspots in powerful streams. Those streams are how magnetars announce themselves to astronomers. A neutron star that suddenly brightens dramatically in X-rays, a star that was quiet and then suddenly emits a blinding pulse, is almost certainly a magnetar with a stressed field releasing energy through its surface. The hotspots are symptoms. The real tension, the real accumulated energy, is still locked inside the crust, and the crust has been accumulating stress since the moment the star was born. The field has been pulling at the rigid iron lattice for centuries, or millennia, tightening the internal stress with every passing year. At some point, no material, however strong, can absorb more stress, and when the crust finally breaks, what gets released makes every human-scale disaster look small. The iron crust of a magnetar has been under stress since the first second of the star's existence. The magnetic field running through it has never stopped pulling. The field wants to drift, to shift its orientation slightly as the interior currents change. The crust, locked into its rigid crystalline structure, holds firm. The tension builds across years, across decades, across centuries. The crust holds firm. And then it does not. The moment the stress exceeds the mechanical strength of the crust, a fracture opens. The crack is tiny by human standards, a split that might measure a fraction of an inch in width. But a fraction of an inch of displacement on a magnetar involves moving material that weighs billions of tons per cubic inch. The amount of energy stored in even a microscopic crack is staggering. The fracture releases that energy all at once, in a fraction of a second. Scientists call this a starquake, a name that correctly implies a parallel to earthquakes on Earth. On Earth, tectonic plates press against each other for centuries, storing elastic energy in the rock, until the stress becomes too great and the rock slips. The slip takes seconds. The energy release shakes cities hundreds of miles away. A starquake follows the same logic, just at a scale that makes Earth's most powerful earthquakes feel like tapping a table. The energy released by a single major starquake exceeds the total amount of energy our Sun will produce over 100,000 years. 100,000 years of solar output released in less than a second from a crack in a crust that you could step over if you were somehow standing next to it. That energy does not stay inside the star. It cannot. The crack sends a shock wave through the entire star, vibrating the crust like a struck bell. The vibration displaces the magnetic field lines anchored in the crust, sending a violent pulse of electromagnetic energy outward from the star. What emerges from the magnetar in the moments following a starquake is a blast of X-rays and gamma rays, the most energetic form of radiation in the universe, fired outward in a concentrated burst that travels at the speed of light in all directions. Near the magnetar, within a few thousand miles, this burst would strip apart any matter it encountered. The radiation would overwhelm the structural bonds of any atom, disintegrating solid material the same way a blowtorch dissolves a paper towel, but instantaneously. From farther away, the burst dims with distance, but even across thousands of light years, the energy remains detectable. Sensitive instruments in orbit around Earth have recorded magnetar starquake bursts from tens of thousands of light years away, and once, in the recorded history of astronomy, a single magnetar starquake briefly changed what the night sky looked like. The record holder was a burst from a magnetar 50,000 light-years from Earth, an object so far away that its light left before modern humans existed, and it was still almost bright enough to damage instruments pointed directly at it. On December 27th of 2004, something happened 50,000 light-years from Earth. A magnetar's crust cracked. The burst of energy that came off that crack took 50,000 years to reach Earth, traveling at the speed of light the entire way. By the time it arrived, the human civilization that recorded it had not existed for most of that journey. The event lasted about 0.2 of a second. In those 0.2 of a second, the magnetar called SGR-1806-20 released more energy than the Sun will produce in the next 250,000 years. The number is almost impossible to hold in your mind. Every second, our Sun converts 4 million tons of mass into pure energy through nuclear fusion. The Sun has been doing this for 4.5 billion years. The magnetar released more energy than 250,000 years of that in the time it takes to blink. The blast hit Earth at 2:30 in the morning Greenwich time. Several spacecraft with instruments designed to detect gamma rays immediately saturated. The burst was so intense that some detectors were simply overwhelmed and shut down, unable to record what they were seeing. Scientists scrambling to analyze the data found that the burst had briefly ionized the upper layer of Earth's atmosphere, the same layer that radio waves bounce off to travel around the planet. From 50,000 light-years away, a starquake partially disrupted Earth's ionosphere. For context, nothing outside our solar system has ever measurably altered Earth's atmosphere before or since. The nearest star to our Sun is about 4 light-years away. This magnetar was 50,000 light-years out, 12,000 times farther than the nearest star, and it still affected the physical layer of gas surrounding our planet. The burst was so bright that it briefly became the most luminous object in the sky outside our solar system, outshining everything except the Sun and Moon. Scientists have studied this event for years and traced it back to the crust fracture model. The starquake released the stored stress from the magnetic field in an explosive discharge. The crust vibrated. The field lurched. The plasma above the surface was energized catastrophically and fired outward. What the event clarified is the scale of what a magnetar can do from an astronomical distance. At 50,000 light-years, the burst was dramatic but not dangerous to life on Earth. It disrupted electronics slightly, charged up the ionosphere, and saturated detectors. Nothing more. The danger zone for a magnetar is much closer. If that same event had happened within a few thousand light-years of Earth, the consequences would have been more serious. Closer still, the question stops being about disrupted ionosphere and becomes a question of survival. Scientists have worked out fairly precisely how close is too close, because the physics of radiation intensity with distance is well understood. The answers are unsettling. The lethal radius of a magnetar event is not measured in miles. It is measured in light years. And before we reach the question of distance and survival, the field itself, even at rest, even without a starquake, does something to human biology that requires no burst of radiation at all. You do not need to be near a starquake to die from a magnetar. The steady, constant magnetic field, the one that is always there between bursts, is sufficient on its own. The minimum safe distance from a magnetar, based on what the field does to matter at various intensities, is roughly 600 miles. 600 miles, New York City to Cleveland. A short domestic flight. At that distance, the magnetic field of a magnetar is strong enough to rip electrons directly out of the atoms in your body. Here is why that matters. Every material on Earth, including human tissue, depends on electrons being in specific positions around atomic nuclei. Electrons are the connective tissue of chemistry. They form the bonds between atoms. They hold molecules together. They are the reason water is liquid, the reason DNA holds genetic information. Pull the electrons out of the atoms, and the chemistry stops. Molecules do not fall apart gently. The bonds that held them together vanish instantly. The atoms, now positively charged because their electrons are gone, repel each other violently. Every molecule in your body disintegrates simultaneously. A human at 600 miles from a magnetar would not be burned or crushed, or torn apart in any mechanical sense. The person would dissolve into a cloud of charged particles in a fraction of a second. The atoms would still be there. The electrons would still be there. They would just no longer be connected to each other. For comparison, Earth's magnetic field is so weak that living inside it for an entire human lifetime has no measurable biological effect. Medical MRI scanners, the strongest magnetic fields most people ever encounter, top out at around 3 Teslas. Some research machines reach 45 Teslas, enough to affect certain biological processes, enough to be treated with caution. A magnetar's field, at 600 miles, would be trillions of times stronger than an MRI machine. There is also a specific effect related to water. Human cells are roughly 70% water. Water molecules are weakly diamagnetic, meaning they generate a tiny opposing magnetic field when exposed to an external field. Under normal conditions, this effect is negligible, barely detectable. In extremely strong magnetic fields, diamagnetic materials experience a repulsive force from the field. Scientists have actually demonstrated this with frogs. A live frog placed in a sufficiently strong magnetic field levitates because the diamagnetic water in its tissues is repelled by the field strongly enough to overcome gravity. The frog is unharmed at that field strength, roughly 16 Teslas. Near a magnetar at 600 miles, the diamagnetic repulsion on the water in human cells would be so extreme that the force tearing the body apart from the inside would be violent and immediate. The water in every cell would be pulled in the direction of decreasing field strength simultaneously, and the forces involved would be far greater than the tensile strength of any biological tissue. Death would occur before any other effect had time to register, and at 600 miles, you have not even gotten close enough to see the surface. What happens as you approach further is a progression of increasingly extreme effects, each layer of proximity introducing a new physical process that dismantles matter more thoroughly than the last. The field does something specific and measurable to every type of matter as its intensity increases. And some of the most extreme effects happen to something that seems indestructible. Metal. Metal is supposed to be tough. Iron, steel, titanium, tungsten. These are the materials humans use when things need to survive extreme conditions. The strongest structural materials ever engineered are metals or metal composites. Spacecraft, nuclear reactor vessels, armor, bridges. When the environment gets brutal, metal is what we reach for. The Magnetar's field does not care. As a metal object enters the increasing field strength near a magnetar, the effects are progressive and total. They begin subtly and escalate to complete destruction before the object gets anywhere near the surface. The first effect, beginning at enormous distances, is induction. A changing magnetic field induces electrical currents in any conductor. As a metal object falls through the gradient of the magnetar's field, the increasing field strength acts like a changing field, and enormous electrical currents begin flowing through the metal. Those currents generate heat. The heat builds faster than any material can dissipate it. At sufficient field strength, the induced currents would vaporize the metal from the inside out. Any spacecraft approaching a magnetar would be destroyed by internal heating long before any mechanical force reached it. Deeper in, the field begins to affect the metal at the atomic level. The iron atoms in a steel hull, like the iron atoms in any material, have electron clouds that the field begins to deform. The spherical electron clouds flatten into cylinders aligned with the field. As the atoms change shape, the crystal structure of the metal changes with them. Metals derive their strength partly from the regular arrangement of their atoms. As that arrangement distorts under the field, the metal softens, warps, and loses its structural integrity. A steel beam that could support a skyscraper would behave like soft clay in the field close to the magnetar surface. The process continues as the field intensifies. Electron clouds shrink and tighten into those needle shapes described earlier. The bonds between atoms weaken until they disappear. The metal ceases to be metal in any meaningful chemical sense and becomes a collection of isolated, deformed atoms with no structural relationship to each other. At the scale of a human-built spacecraft, the progression from conducting solid to disintegrated cloud would take place over a distance of a few hundred miles, measured from the 600-mile danger line inward. A probe launched toward a magnetar would not survive to take a single close-range measurement. This is a genuine problem for astronomers who want to study magnetars directly. Every instrument we have ever used to study space is material-based. Telescopes, antennae, detectors, all of it is made of matter that would be destroyed long before approaching a useful observing distance. The information we have about magnetars comes exclusively from distant observations, X-ray telescopes in orbit around Earth, radio telescopes on the ground, and gamma-ray detectors on satellites. Every detail known about the interior, the crust, the starquakes, the field structure, comes from interpreting signals that traveled thousands of light-years before reaching a safe instrument. And some of those signals carry evidence of the most extreme temperatures found anywhere in the observable universe. Not the temperature of the surface, the temperature of the material ejected during a starquake, superheated plasma fired outward from the crust fracture, carrying energy dense enough that measuring its heat requires units that have no practical meaning on Earth. The numbers waiting in the next chapter are some of the most extreme in astronomy. When the crust of a magnetar cracks, the energy does not all escape as radiation. Some of it heats the plasma immediately above the fracture to temperatures that challenge the imagination. Plasma is the fourth state of matter, a gas so hot that electrons have been stripped away from atoms entirely, leaving a soup of charged particles. Stars are plasma. Lightning is plasma. The surface of the sun reaches temperatures of roughly 10,000 degrees Fahrenheit. The interior of the Sun reaches about 27 million degrees. A nuclear bomb detonation reaches temperatures of roughly 180 million degrees in the first microseconds of the explosion. The plasma ejected during a major Magnetar starquake reaches temperatures on the order of billions of degrees. The Sun at its center produces energy through nuclear fusion, the same process that powers hydrogen bombs. The plasma near a Magnetar starquake is so hot it exceeds the conditions needed for most types of nuclear fusion to occur naturally. The temperature is high enough that particle collisions happen with enough energy to produce exotic particles that are normally only found in particle accelerator experiments. At these temperatures, matter does not behave like gas, or plasma, or anything with a familiar name. The particles collide so frequently and with such force that even the concept of temperature, normally defined as the average energy of particles in a collection, starts to break down at the edges because the energy distribution becomes extreme. The fireball itself is short-lived. The Magnetar's intense gravity pulls most of the ejected material back toward the surface within seconds. But in those seconds, the fireball radiates energy at a rate that temporarily makes the Magnetar one of the brightest objects in the observable universe. The X-ray and gamma-ray pulse that reaches Earth from a starquake carries the signature of this fireball. By analyzing the spectrum, the distribution of energies in the radiation, scientists can work backward to calculate the temperature of the source. Those calculations have consistently produced numbers in the billions of degrees range for major bursts. For comparison, the core of the most massive stellar explosions, giant supernovae, reach temperatures of roughly 200 billion degrees. Magnetar starquake fireballs sit in a comparable range, produced not by the death of a star, but by the cracking of a crust layer less than a mile thick. The violence is disproportionate. A crack in a thin shell produces temperatures matching the death of stars. This disproportionate violence comes directly from the magnetic field. The field stored energy in the crust, stressed the way a spring stores energy when compressed. When the spring releases, it converts all that stored potential energy into kinetic energy instantly. The Magnetar's crust is the spring, and billions of years of continuous pressure from a magnetic field, 100 billion Teslas strong, has wound it very tight. The spring does not release gently, and after it releases, the Magnetar does not go quiet. The field begins rebuilding its stress in the crust almost immediately. Over the following days, weeks, or months after a major burst, a Magnetar typically enters a period of increased activity, smaller cracks opening in the freshly stressed crust, firing additional bursts of decreasing intensity. Scientists call this a burst storm, a barrage of smaller starquakes following a major event, the crust resettling into a new stress configuration. The storm eventually quiets, the crust stabilizes into its new shape. The field begins building tension again, until the next crack. But over thousands of years, each crack takes something away from the Magnetar that it can never recover. A Magnetar does not last forever. The magnetic field that defines everything about it, the field that deforms atoms, splits light, and fires starquakes across the galaxy, is slowly decaying. It has been decaying since the moment the star was born, and after about 10,000 years of activity, it will be gone. 10,000 years sounds like a long time, but in cosmic terms, it is almost nothing. The Sun has been burning for 4.5 billion years. The universe has been running for about 13.5 billion years. A Magnetar's violent phase is a brief flash by comparison, equivalent to about 3 minutes in the life of a 40-year-old human. The decay happens because the magnetic field loses energy every time it does anything. Every starquake converts field energy into radiation. Every X-ray burst pulls energy from the field. Every time the field heats the surface, and that heat radiates into space, energy leaves and does not return. The dynamo that created the field in the first 10 seconds of the star's life is no longer running. There is no source of new energy to replace what gets lost. The process is called magnetic field decay, and it follows a gradual curve. Early in the magnetar's life, the field is strongest, the starquakes are most violent, and the X-ray luminosity is highest. As decades become centuries and centuries become millennia, the field weakens incrementally. The starquakes become less frequent and less powerful. The surface cools, the X-ray emission dims. After roughly 10,000 years, the field has weakened to the point where the magnetar transitions into an ordinary neutron star. Quiet, still incredibly dense, still spinning, but no longer capable of the extreme events that defined its early existence. The transition is gradual enough that astronomers can observe magnetars at different stages in their decay. Young magnetars, a few hundred years old, are the most active and the most dangerous. Middle-aged magnetars, a few thousand years old, show decreasing burst frequency. The older examples are quieter still. Their fields weaken to the point where they barely qualify for the classification. What remains after the decay is a standard neutron star, destined to spend billions of years cooling and fading, eventually becoming a cold, dark, dense remnant that emits almost nothing. The 10,000-year window of magnetic fury produces, in total, an enormous amount of energy. Summing the energy of all the starquakes, all the X-ray bursts, all the surface radiation across the full active lifetime of a magnetar gives a number comparable to the total energy output of the Sun over millions of years, concentrated into a 10,000-year window from an object 12 miles wide. The decay also has an implication for what we can study. Every magnetar we can currently observe is living through its active phase. The objects that have already decayed into ordinary neutron stars are no longer identifiable as former magnetars by observation alone. The field that defined them is gone. The signature is erased. Scientists estimate that a significant fraction of the neutron stars currently catalogued as ordinary may actually be former magnetars in their quiet phase. Their violent history is completely hidden. The universe may contain far more of these objects than we can currently count, and the questions surrounding them deepen the more you look. The decay is understood in broad strokes, but the details of how the field dissipates through the interior, how the superfluid core responds as the field weakens, and what happens to the quark matter hypothesis as the internal pressure gradually changes with cooling. All of that remains an active area of research. What we know for certain is that every magnetar currently visible is on a clock, and the countdown began the moment it was born. The magnetar has been fighting itself since birth. On one side, the magnetic field, 100 billion teslas of force, constantly shifting, constantly pulling at the material around it, trying to reorient, trying to move. On the other side, the crust, 10 billion times harder than steel, locked into a crystal lattice that refuses to budge. This is not a fast war. It plays out over centuries. The field exerts pressure on the crust continuously, the way a river exerts pressure on a dam. The dam holds. The pressure builds. Year after year, decade after decade, the stress accumulates in the iron lattice, storing energy the way a compressed spring stores energy, waiting. The technical term for what is happening inside the crust is magnetoelastic stress. The magnetic field and the elastic properties of the crust are in direct conflict. The field applies a twisting, stretching force to the lattice. The lattice resists with its full mechanical strength. The difference between the applied force and the resistive force is the stress, and it grows. Scientists have modeled this process using the same mathematics that describe tectonic plate stress on Earth. The parallel is remarkably close. On Earth, two plates press against each other at a fault line. The rock at the boundary stores elastic energy. When the stress exceeds the breaking strength of the rock, the fault slips. The stored energy releases as seismic waves and heat. On a magnetar, the fault line is the entire crust. The stress is not localized to a narrow boundary, but distributed across the full surface of the star. When the crust finally slips, even a tiny displacement, The seismic wave propagating through the star carries energy that dwarfs anything Earth produces. There is also a feedback effect that makes the situation more complex. When the crust cracks, the field lines anchored in the crust move with the crack. That sudden motion in the field generates a pulse of electromagnetic radiation, which is the gamma-ray burst. But the motion also changes the local field structure around the crack site. The field in that region has now shifted slightly, and the new configuration exerts a different stress pattern on the surrounding crust. The crack can trigger additional cracks nearby, each one releasing its own pulse. This is why magnetar bursts often come in clusters rather than single isolated events. What scientists found particularly striking when they modeled this is that the crust never fully relaxes. Even after a major starquake, the field continues pressing. The stress builds back up. The crust is always somewhere on the spectrum between a fresh fracture and the next breaking point. The magnetar is always at war, and the war has no peace treaty. What makes this especially interesting is the timescale. On Earth, major earthquakes at a given fault line might be separated by hundreds or thousands of years. On a magnetar, major bursts can repeat on timescales of months to years. The field is so powerful and the crust stress reloads so quickly that the star is almost continuously active during its early life. This constant activity means the magnetar is constantly dumping energy into space, constantly losing field strength, constantly aging, and the war, for all its violence, is slowly winding down. But before the field weakens, it does something to the space around the magnetar that goes beyond splitting light and deforming atoms. It creates a physical barrier, an envelope of charged particles and radiation that surrounds the star and shapes everything that tries to pass through it. That envelope has its own strange physics, and understanding it changes how scientists think about what lives in the vicinity of the most magnetic objects in the universe. Every magnetar is surrounded by a shell of trapped energy. The magnetic field does not stop at the star's surface. It extends outward into space, weakening with distance but still present across thousands of miles. Within that extended field, charged particles and photons behave very differently from how they behave in open space. This region is called the magnetosphere, and for a magnetar, it is one of the most hostile environments in the universe. On Earth, we have a magnetosphere too. It is the invisible magnetic bubble that surrounds our planet, extending tens of thousands of miles into space. Earth's magnetosphere deflects the solar wind, the constant stream of charged particles flowing outward from the sun. Without it, the solar wind would slowly strip away our atmosphere over millions of years. The magnetosphere is the shield that makes long-term life on Earth possible. A magnetar's magnetosphere works on an incomparably larger scale, and it does the opposite of sheltering anything. The field is so powerful that charged particles entering it are seized immediately and funneled along the field lines toward the magnetic poles. As they travel, they accelerate rapidly. The field lines converge at the poles like a funnel, and the particles screen down that funnel, gaining energy every fraction of a second. When they hit the polar regions of the magnetar's surface, they hit hard enough to generate X-rays. The poles of a magnetar glow continuously in X-ray light, fed by this constant stream of incoming particles funneled from the surrounding space. The magnetosphere also traps radiation. X-ray photons emitted from the surface do not simply fly outward into space. Many of them are captured by the field, bent back toward the star, and undergo multiple scatterings before finally escaping. The result is that the magnetosphere acts as a kind of radiation blanket, reshaping the spectrum of light that eventually escapes and making it look different from what was originally emitted at the surface. Scientists have to account for this effect when studying magnetar spectra. The light they receive has been filtered through the magnetosphere, and decoding that filter requires modeling the particle and radiation physics of the entire extended field region. There is a boundary to the magnetosphere called the light cylinder. At a certain distance from the magnetar, The rotation of the field lines would require material co-rotating with them to move faster than the speed of light. Since nothing can do that, the magnetosphere has a hard outer boundary where the field structure changes character fundamentally. Beyond the light cylinder, the field becomes open into the wider galaxy. Particles and radiation escaping past this boundary are free. They travel outward at the speed of light and eventually become the signals that detectors on Earth pick up. The magnetosphere also shapes the radio waves that some magnetars emit. Pulsars, which are rapidly rotating neutron stars, including some magnetars, sweep beams of radio waves across space like a lighthouse. Each rotation brings the beam briefly into alignment with Earth, producing a regular pulse that astronomers can time with extraordinary precision. Magnetars that emit radio pulses are particularly valuable to study because the pulses carry information about the magnetosphere they passed through. The timing, polarization, and frequency distribution of the radio pulses encode the properties of the field that shaped them. Some magnetars change their pulse timing abruptly, a sign that the internal field structure has shifted, likely due to a subsurface starquake too small to produce a visible burst. The magnetosphere is, in a sense, the magnetar's public face. It is the boundary between the extreme interior physics and the wider universe. And some of the strangest physics visible from outside the star happens right at that boundary, where the field is just weak enough for matter to survive, but strong enough to twist it into entirely new configurations. Here is a thought experiment that makes the numbers real. The Moon orbits Earth at an average distance of about 239,000 miles. It exerts a gravitational pull on Earth's oceans, creating tides. It reflects sunlight at night. It has been orbiting our planet for about 4.5 billion years, and its effects on Earth are gentle and predictable. Now replace the Moon with a magnetar. The results begin immediately, and they do not stop. At 239,000 miles, the magnetar's magnetic field, while far weaker than at its surface, is still incomparably stronger than anything Earth's technology has ever produced. The field at that distance would be strong enough to instantly erase every magnetic storage device on Earth. Every hard drive, every credit card magnetic stripe, every MRI machine calibration, every data center running on magnetic storage would be wiped simultaneously, without warning, in the first second. That is the subtle effect. The field would also begin pulling on the iron in Earth's core. Earth's core contains an enormous amount of liquid iron, generating our own magnetic field. The magnetar's field would interact with that iron, inducing currents, generating heat, and potentially destabilizing the dynamo that keeps our magnetic shield running. Over time, our protective field could weaken. The charged particle environment near Earth would change completely. The magnetar's magnetosphere extends far beyond the distance between Earth and Moon. Earth would be inside the magnetar's magnetosphere, exposed to the constant stream of accelerated charged particles that bombard the magnetar's poles. Our atmosphere would be subjected to radiation levels that exceed anything it experiences from the Sun. The Moon's gravitational effect on Earth's oceans produces tides of a few feet. A magnetar at the same distance, while similar in mass to the Moon, would produce tides shaped by both gravity and the enormous magnetic tidal force on Earth's iron core. The dynamics would be unpredictable and severe. And then there is the starquake question. A magnetar sitting 239,000 miles from Earth is well inside the zone where a major starquake would be catastrophic for life. The December 2004 burst, from 50,000 light-years away, disrupted Earth's ionosphere. A comparable burst from inside the Moon's orbit would deliver radiation intense enough to strip the atmosphere. The thought experiment demonstrates something important about context. The same object that we can safely study from light years away, that we can observe and analyze and write chapters about, becomes an extinction-level scenario when placed at a distance that would otherwise be utterly unremarkable. The danger is not in the existence of magnetars. They are far away, The nearest known magnetar is roughly 6,000 light-years from Earth, safely beyond any hazard range. The danger lives in the thought experiment itself, in what it reveals about the gap between safe observation and proximity. There is no middle ground with a magnetar. There is safe distance, and there is death. And this extreme contrast between observation and proximity applies to the entire question of what magnetars have taught us about physics. Scientists studying them are safe. The knowledge they gain is extraordinary. But gaining that knowledge has required building new tools, designing new approaches, and in some cases completely revising ideas about how matter works. The instruments that first caught a magnetar's signal had no idea what they were looking at. Nobody was looking for a magnetar when they found the first one. In March of 1979, a burst of gamma rays hit several spacecraft almost simultaneously. The burst was so intense that it saturated instruments designed to record the most energetic events in the universe. The pulse lasted about 0.2 of a second, the same duration as the famous 2004 event. And then it was followed by a longer pulsating tail of X-rays that repeated with a period of about 8 seconds. Scientists were baffled. Gamma-ray bursts had been detected before, but they came from random directions in the sky, brief flashes, without any repeating pattern. This event came from a specific, identifiable location, and it repeated. The location turned out to be the Large Magellanic Cloud, a small galaxy neighboring our own, about 160,000 light-years away. The source was inside the remnant of a recent supernova. Something at that location had produced an event energetic enough to be detected across 160,000 light-years, with instruments that were barely sensitive enough to record it. Over the following years, more events came from the same location. The source kept firing bursts, none as powerful as the first, but all coming from the same spot in the sky. Scientists classified it as a soft gamma repeater, a category defined purely by observation, a source of repeated, relatively soft gamma-ray bursts from a fixed position. The theoretical explanation came separately. In 1992, two physicists named Robert Duncan and Christopher Thompson published a paper proposing the magnetar model. They described exactly the kind of object that would produce the observed behavior. A highly magnetized neutron star with a stressed crust firing bursts as the crust cracked. The model matched the observations. The connection between the theoretical magnetar model and the observed soft gamma repeaters was confirmed over the following decade as more sources were found and their properties studied in detail. What made the original detection remarkable, in retrospect, is how many things had to be in place for it to happen at all. The burst needed to be energetic enough to reach Earth across 160,000 light-years. The spacecraft in orbit needed to be sensitive to gamma rays. The multiple spacecraft needed to be positioned so that the slight timing difference in when the burst reached each one could be used to triangulate the source direction. Any one of those conditions missing and the first magnetar detection would have slipped by unnoticed. The discovery was partly skill and mostly luck, which is how many of the most important discoveries in astronomy work. Since that first detection, dozens of magnetars have been identified, and the tools used to study them have grown significantly more powerful. But every detection shares the same constraint. All of it happens from an enormous safe distance. All of it is interpretation of signals that have traveled for thousands or hundreds of thousands of years before reaching an instrument. The information is real and detailed. The proximity is zero. And the closer scientists look at the data, the more questions appear that the data alone cannot answer. Some of those questions touch on things that have no answer yet, because the physics required to answer them may not yet exist. Magnetars sit at the edge of what physics can currently describe. Every major branch of physics contributes something to understanding them. General relativity handles the extreme gravity. Quantum mechanics handles the behavior of particles in extreme fields. Nuclear physics handles the dense interior. Electromagnetism handles the field itself. Thermodynamics handles the heat and energy flow. The problem is that none of these branches was built to work together in the conditions a magnetar produces. They were developed and tested in regimes far removed from 100 billion Tesla magnetic fields, densities of hundreds of millions of tons per cubic inch, and temperatures of billions of degrees. When scientists apply the equations to a magnetar, the calculations work individually, in pieces. But combining them into a complete, unified description of a magnetar from crust to core runs into conflicts and gaps. The equations start pulling in different directions in the overlap zones. The interior of a magnetar is the most direct example. The outer crust is described reasonably well by condensed matter physics, the physics of solid materials. The outer core is described by nuclear physics and superfluid dynamics. The inner core, where quark matter might exist, but the boundary regions between these zones, where one type of physics transitions into another, involve conditions that none of the individual frameworks handles cleanly. Scientists call this the equation of state problem. The equation of state is the relationship between pressure, density, and temperature for a given material. On Earth, the equation of state for water or air or steel is well known. For the material in a magnetar's inner core, under pressures and densities never recreated in a laboratory, the equation of state is genuinely unknown. Different theoretical models produce different predictions for what the inner core looks like, and the predictions disagree significantly. Some models predict a uniform superfluid of neutrons all the way to the center. Others predict a transition to quark matter at a certain depth. Others predict exotic intermediate states with names like nuclear pasta, where the protons and neutrons are arranged in sheets, cylinders, and bubbles rather than discrete particles. Nuclear pasta is not a whimsical name. It describes a real theoretical prediction. At densities between the outer core and inner core, the competition between nuclear attraction and electrostatic repulsion may produce material that organizes itself into layered sheets like lasagna, or cylindrical tubes like spaghetti, or spherical bubbles like gnocchi. The shapes would have real consequences for how heat and electricity move through the star. Distinguishing between these models requires observations that are difficult to make. Gravitational wave detectors offer one path. When two neutron stars collide and merge, they produce gravitational waves whose shape depends on the equation of state of the material inside. The signal carries information about how the stars deform during the merger. The detection of gravitational waves from a neutron star merger in 2017 gave scientists their first direct measurement of how neutron star material behaves under the extreme stress of a collision. It constrained some models and eliminated others, but the inner core question remains open. The mystery at the center of a magnetar is connected to one of the most fundamental unanswered questions in all of physics. What happens to matter at the absolute highest pressures that nature can produce? And does the answer change what we think we know about the particles that build everything? Those questions lead directly to the deepest mystery the magnetar presents. Everything you have ever touched is made of atoms. Atoms are made of protons, neutrons, and electrons. Protons and neutrons are made of quarks. Quarks are, as far as current science can determine, fundamental. They cannot be broken down further. Under ordinary conditions, quarks are permanently confined inside their parent particles. A quark has never been observed in isolation, in any experiment, anywhere. No particle accelerator on Earth has ever produced a free quark that existed long enough to be measured independently. Quarks come in groups of 2 or 3, locked together by a force called the strong nuclear force, and that force actually gets stronger the farther apart the quarks are pulled. Trying to separate quarks is like stretching a rubber band. The harder you pull, the harder it pulls back. Inside the core of a magnetar, scientists suspect that confinement might break down. The pressure at the center of a magnetar is so extreme that the individual neutrons are pressed together until their boundaries blur. At these densities, a quark inside one neutron is physically as close to a quark inside a neighboring neutron as it is to its own partners. The confinement force loses its grip because there is no meaningful distinction between inside and outside a particle anymore. The result if the theoretical models are correct, is quark matter, a state where quarks move freely through the material, shared across the entire volume rather than locked inside individual particles. The boundary between one neutron and the next dissolves completely into a continuous quantum fluid of quarks. Quark matter has been produced briefly in particle accelerators by smashing heavy atomic nuclei together at nearly the speed of light. The collisions recreate temperatures and densities that existed a fraction of a second after the Big Bang, conditions extreme enough to briefly free quarks from their confinement. The quark-gluon plasma produced in these collisions lasts for a tiny fraction of a second before cooling and recombining into ordinary particles. A magnetar core would sustain those conditions permanently. Some theorists add a further complication. The quarks that make up ordinary protons and neutrons are called up quarks and down quarks. Under the pressures of a magnetar core, a third type of quark, the strange quark, might become energetically favorable. Strange quarks are heavier than up and down quarks, but at sufficient pressure they cost less energy to produce than the alternative of adding more up and down quarks. If strange quarks appear in the core, the material becomes strange quark matter, and strange quark matter has a theoretical property that is genuinely alarming. Some models suggest it might be more stable than ordinary nuclear matter. More stable in this context means that it would be the lowest energy state of matter at any pressure, including zero pressure. If a chunk of strange quark matter were ever exposed to ordinary nuclear matter at low pressure, the ordinary matter might begin converting into strange quark matter spontaneously, releasing energy as it converts. The idea that strange quark matter could be contagious to ordinary matter, that contact with it could convert normal atoms into a spreading blob of something entirely different, earned the nickname strange nuggets, or strangelets. The hypothesis has been discussed seriously in physics literature for decades. The good news is that the conversion, if it happens at all, likely requires conditions found only inside magnetar cores. The strange quark matter hypothesis, though scientifically serious, remains unconfirmed. No observation has yet proven or disproven it, but the fact that it is a serious scientific hypothesis, published in peer-reviewed journals and taken seriously by physicists who study extreme matter, says something about the territory a magnetar occupies. It is the place where physics is still writing its own rules. A magnetar does not just host extreme magnetic fields, it also produces some of the most extreme gravitational conditions in the universe. Short of a black hole, the surface gravity of a magnetar is roughly 200 billion times stronger than Earth's. That number affects how we understand gravity itself, because it takes general relativity, Einstein's theory of gravity, into a regime where its predictions can actually be tested against reality. On Earth, general relativity produces effects so small they require the most sensitive instruments ever built to detect. The gravitational time dilation near Earth's surface, the effect where time runs slightly slower close to a heavy object, is measurable, but tiny. GPS satellites have to account for it in their calculations, or the navigation error would accumulate over time. But the correction factor is small enough that it took decades of technological development to confirm it directly. Near a neutron star, the same effect becomes dramatic. Time at the surface of a neutron star runs measurably slower than time at a safe distance. A clock on the surface of a magnetar would run roughly 30% slower than a clock far away from the star. If you could somehow observe a process happening on the magnetar's surface from Earth, it would appear stretched out in time, every event slowed down by the gravitational time dilation. Light climbing out of a magnetar's gravitational well loses energy as it fights the pull of gravity. This is called gravitational redshift. The photons that leave the surface with a certain energy arrive at distant observers with slightly less energy, shifted toward the red end of the spectrum. By measuring this redshift in the X-ray emissions from neutron stars and magnetars, scientists can calculate the mass-to-radius ratio of the star. That ratio is a direct test of the equation of state. A stiffer equation of state, one where the matter resists compression more strongly, produces a larger radius for a given mass. A softer equation of state produces a smaller, denser star. The gravitational redshift measurements, combined with mass measurements from binary star systems, place constraints on which equations of state are physically allowed. Magnetars have also contributed to testing an aspect of general relativity called frame dragging. A massive spinning object does not just warp the space around it with its gravity, it drags the space itself around with its rotation, like a spinning ball dragging honey. Near a rapidly spinning magnetar, space is literally rotating, carried along by the star's spin. Any object in orbit near the magnetar, any particle or photon, has its path subtly twisted by this dragged space. Frame dragging was confirmed in Earth orbit using precision gyroscopes, but the effect near Earth is incredibly small. Near a neutron star spinning dozens of times per second, the effect is orders of magnitude larger and directly detectable in the timing of pulsar signals. Every test of general relativity near extreme compact objects comes back consistent with Einstein's equations. So far, no experiment or observation at any level of gravity has found a deviation from general relativity's predictions. But scientists expect that somewhere between neutron star conditions and black hole conditions, the theory will eventually break down or require modification. The singularity inside a black hole, where general relativity's equations produce infinities that signal a breakdown of the theory, is the obvious candidate. Magnetars sit on the safe side of that boundary, just barely. And the question of what sits on the other side of that boundary connects the study of magnetars directly to the most famous and most extreme gravitational objects in physics. A magnetar is the most extreme object in the universe that is still made of matter. That sentence contains an important qualifier: still made of matter. A black hole is more extreme in almost every measurable way. Its gravity is stronger, its density is higher, its effects on surrounding space are more severe, but a black hole, at its center, according to general relativity, has collapsed to a point where the concept of matter as a physical substance breaks down entirely. The physics stops, the equations produce infinities and refuse to continue. A magnetar has not crossed that line. Its interior is strange and extreme, and largely mysterious. But neutrons still exist inside it, at least in the outer core. Atoms, severely deformed, still exist on its surface. The star still has a surface, it still has a crust, it has structure that can be described, modeled, and tested against observations. The dividing line between a magnetar and a black hole is mass. A neutron star can only hold itself up against its own gravity if its mass stays below a certain limit. This limit is called the Tolman-Oppenheimer-Volkoff limit, and it sits somewhere between 2 and 3 times the mass of our Sun, depending on the equation of state of the material inside. Below the limit, the neutron degeneracy pressure, the quantum mechanical resistance of neutrons to being compressed into the same space, is strong enough to hold the star up. Above the limit, gravity wins. The star collapses further, past neutron star densities, past quark matter densities if they exist, and continues collapsing until it forms a black hole. A magnetar sits below that limit, comfortably enough that the most massive known magnetars are still a safe distance from the collapse threshold. But the proximity matters intellectually. A magnetar is the closest analog to a black hole that still permits direct study through electromagnetic signals. The physics inside a magnetar operates at the edge of the regime where matter stops behaving like matter. The equation of state questions, the quark matter hypothesis, the superfluid and superconductor models, all of them are steps toward understanding what happens inside matter as it approaches the collapse threshold. Understanding magnetars better is one path toward understanding what happens just before a black hole forms. And there is a direction of inquiry that goes the other way. If we study what is known about the interior of a magnetar and extrapolate toward higher and higher densities, the extrapolation eventually reaches conditions where general relativity predicts a singularity. The physics breaks. What fills the gap between what a magnetar contains and what a singularity represents is one of the central unsolved problems in theoretical physics. Some researchers believe that a correct quantum theory of gravity, which does not yet exist, would remove the singularity and replace it with something physical, a final state of matter at extreme density that does not collapse to infinity. If that final state exists, its properties might share something with quark matter or strange quark matter inside magnetar cores. The most extreme magnet in the universe and the most extreme gravitational object in the universe may be connected through the same unanswered questions about the deepest structure of matter. Scientists cannot visit a magnetar. They cannot send a probe. They cannot collect a sample. Every measurement ever made of a magnetar has been made from thousands of light years away, interpreting radiation that took millennia to arrive. And yet magnetars have produced more tests of fundamental physics than almost any other object in the universe. The vacuum birefringence confirmation came from a neutron star, not a magnetar, but operating on the same principle. The gravitational redshift measurements have constrained the equation of state. The gravitational wave merger observations have placed limits on the interior structure. The X-ray timing of burst storms has revealed internal dynamics that no Earth-based experiment could replicate. What makes magnetars useful as laboratories is the extreme range of conditions they produce. A laboratory on Earth can test physics at room temperature and pressure, or push to the limits of particle accelerator energies. A magnetar produces magnetic fields, densities, temperatures, and pressures that exceed anything on Earth by many orders of magnitude simultaneously. Testing physics at those extremes requires the universe itself to be the laboratory, and magnetars are the most extreme controlled experiments the universe runs, controlled in the sense that they are stable, persistent objects rather than brief collisions or explosions. The study of magnetar X-ray spectra has revealed specific spectral features that carry direct information about conditions at the surface. Absorption lines in the X-ray spectrum correspond to specific transitions of atoms or ions in the strong magnetic field, and their exact energies depend on the field strength. By measuring those lines, scientists can map the field directly from light years away. Radio observations of magnetars that emit pulsar-like pulses have revealed something unexpected. Some magnetars switch between radio loud and radio quiet states over timescales of weeks to months. The switch appears to correlate with changes in the internal field configuration, changes that are invisible directly but reveal themselves through the altered radio pulse shape. This switching behavior has no simple explanation and remains an active research problem. It suggests that the interior of a magnetar is not static between starquakes, but is constantly reorganizing in subtle ways, occasionally producing a configuration that allows radio emission and then shifting away from it. The tools used to study magnetars have also advanced significantly since the first detection. The current generation of X-ray space telescopes can resolve timing features in magnetar bursts down to fractions of a millisecond, timescales that correspond to physical processes happening just a few dozen miles across the star. The telescopes cannot see the surface directly, but they can effectively listen to the star's heartbeat with extraordinary precision. Future instruments promise better still. Proposed X-ray telescopes with larger collecting areas and better energy resolution would allow detection of weaker spectral features, tighter constraints on the equation of state, and potentially the identification of features predicted by quark matter models that current instruments cannot distinguish. The laboratory in the sky is producing results, and each result raises new questions that push closer to the boundaries where the known physics stops. Those boundaries are not just the edge of what magnetars have taught us, they are the edge of what any object in the universe has taught us. And one question in particular keeps surfacing every time scientists push the magnetar models to their limits. The early universe was a magnetar. Not in a literal sense. The Big Bang did not produce a single compact object, but the conditions that existed in the first fractions of a second after the Big Bang, the temperature, the density, the behavior of matter and energy, bear a striking resemblance to the conditions inside a magnetar core. In the first microsecond after the Big Bang, the universe was so hot and so dense that quarks moved freely, unconfined inside particles, in a state called the quark-gluon plasma. Protons and neutrons had not yet formed. The fundamental building blocks of matter existed as a hot, dense soup without structure. A magnetar core, if the quark matter hypothesis is correct, sustains a cold version of that same state permanently. Not hot plasma, but a dense, zero-temperature quantum fluid of quarks. The conditions are different in important ways, but the freedom of quarks from confinement is the same fundamental phenomenon. This connection gives magnetar research an unexpected relevance to cosmology, the study of the origin and evolution of the universe. One of the open questions in cosmology is exactly how and when quarks first became confined into protons and neutrons as the early universe cooled. This phase transition happened when the universe was about a microsecond old and cooled past a certain temperature. The details of that transition, whether it was smooth or abrupt, whether it produced density fluctuations that left marks on the large-scale structure of the universe, depend on the equation of state of quark matter, the same equation of state that determines what is happening in the center of a magnetar today. By studying magnetar cores indirectly through their observable properties, scientists are effectively probing the same physics that govern the universe at a microsecond old. The two regimes are different in temperature and origin, but share the same fundamental questions about quark behavior. There is also a connection through magnetic fields. The universe today contains magnetic fields at every scale, from the fields around planets to fields spanning entire galaxy clusters. Where these large-scale magnetic fields came from is an unsolved problem. The leading hypothesis involves processes in the early universe that generated small seed fields, which were then amplified by the motion of conducting plasma over billions of years. Magnetars represent the extreme end of this amplification process, a natural dynamo that takes a seed field and multiplies it by a factor of 1,000 in 10 seconds. Understanding that dynamo mechanism in detail may illuminate the broader question of how magnetic fields are generated and sustained across cosmic scales. The physics of the most magnetic objects in the current universe connects back to the physics of the universe at its birth. That connection runs deeper than analogy. It runs through the shared equations that describe how matter behaves at the edge of what is known. And at the very frontier of those equations, there is one question that magnetar research has made more urgent than ever. The most fundamental question a magnetar raises is not about magnetic fields, or starquakes, or quark matter. It is about the nature of matter itself. Everything humans have ever touched, built, measured, or eaten is made of atoms. Atoms are made of protons, neutrons, and electrons. Those particles are held together by four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. The rules governing these forces have been tested in laboratories for over a century. The tests agree with the theory to extraordinary precision. The theory is called the Standard Model of Particle Physics, and it is one of the most successful scientific theories ever developed. It predicts the outcomes of particle collisions with accuracy to many decimal places. It correctly described particles before they were discovered. It is, within its tested range, almost certainly correct. The problem is that the Standard Model was built and tested in a very narrow range of conditions: room temperature, particle accelerator energies that, while high, are still far below the densities of a magnetar interior. The Standard Model has never been tested at the pressure found in the deep core of a neutron star. It has never been tested in a magnetic field of 100 billion teslas. Physicists assume the Standard Model holds under those conditions. The assumption is reasonable because the model has held everywhere it has been tested, but assumption and confirmation are different things. A magnetar is the closest thing the universe offers to a test of the Standard Model at conditions it was never designed for. If the behavior of matter inside a magnetar deviates from what the standard model predicts, the deviation would show up in the observable properties of the star. Unexpected spectral features, anomalous cooling rates, gravitational wave signals from mergers that do not match theoretical templates. So far, every observation of magnetars has been consistent with existing theory within the limits of current instrument sensitivity. No clear deviation has been detected. But sensitivity matters enormously here. The observations are still limited by the instruments available. A deviation from the standard model at magnetar densities might be subtle enough that current telescopes cannot resolve it. The next generation of instruments, with higher collecting areas and sharper energy resolution, might see something current tools miss. The possibility that a sufficiently extreme physical regime could expose the limits of known physics is not science fiction. The history of physics is a history of extending into new regimes and finding surprises. Classical mechanics worked perfectly until experiments reached speeds close to light, and then it failed, replaced by relativity. Relativity worked perfectly until experiments reached quantum scales, and then it required quantum mechanics. Every time physics has been pushed into a genuinely new regime, something unexpected has appeared. Magnetar cores represent a genuinely new regime. They are not just the extreme end of a known spectrum. They involve conditions that no theory has been directly verified against. Something unexpected may be waiting in the data, in measurements precise enough to see it. Or the standard model may hold perfectly, which would itself be a remarkable result, a theory validated under the most extreme conditions the universe produces naturally. Either answer changes what we know about the deepest structure of reality. For every magnetar scientists have detected, there may be dozens they have not. Detection requires luck of geometry. A magnetar that never happens to fire a burst during the observation window of an Earth instrument goes unnoticed. A magnetar whose starquake beams its radiation in a direction that does not intersect with Earth gets no notice. A magnetar that has already decayed into an ordinary neutron star looks identical to any other neutron star. The known population of magnetars numbers around 30 confirmed objects. The estimated true population in the Milky Way galaxy alone runs into the hundreds or possibly thousands. Most of those objects are invisible to current instruments. This matters beyond being a statistical footnote. If hundreds of former magnetars exist in the galaxy, invisible and indistinguishable from ordinary neutron stars, then the galaxy has been shaped by far more magnetar activity than the current detection count suggests. Hundreds of starquakes, gamma-ray bursts, and intense radiation events that influence the surrounding interstellar medium, compressed gas clouds, possibly affected conditions in nearby star-forming regions. The history of the galaxy has a magnetar contribution that is currently invisible. There is also the question of magnetars outside the galaxy. The famous 2004 burst came from 50,000 light-years away, near the edge of our galaxy. Similar objects exist in other galaxies. The magnetar that produced that burst was detected despite the extreme distance, purely because the burst itself was so energetic. Weaker bursts from magnetars in nearby galaxies would not be detectable with current instruments. Instruments planned for the next decade may change that. Proposals for X-ray observatories with much larger collecting areas would push the detection threshold low enough to catch fainter bursts from greater distances. If those instruments are built, the population of known magnetars could increase dramatically. More detected magnetars means more data points for the equation of state models, more burst storms to study for crust physics, more gravitational redshift measurements for mass-radius relationships. The size of the known population is currently a limiting factor in the statistical precision of every measurement. There is another category of invisible magnetar that deserves mention. A magnetar buried at the center of a dense cloud of gas and dust is shielded from X-ray observation because the intervening material absorbs the radiation. The galactic center, a region of the Milky Way where star formation and stellar density are both high, is one such shielded environment. Several objects near the galactic center have been detected as magnetars only because they emitted bursts powerful enough to penetrate the shielding. The number of magnetars embedded in the galactic center that have not yet fired a detectable burst is completely unknown. The known universe contains 30 confirmed magnetars. The actual universe contains an unknown and likely much larger number, distributed through every galaxy, many of them hidden by geometry, or shielding, or the passage of time into quiet neutron star retirement. The ones we can see have already upended multiple branches of physics. The ones we cannot yet see may carry answers to questions physicists have not yet thought to ask. A magnetar is silent. Space carries no sound. Sound is a pressure wave, and pressure waves require a medium, something to compress and rarefy as the wave passes through. The vacuum of space between stars has essentially no medium. Sound produced on the surface of a magnetar dies within a few inches of the star, swallowed by the near vacuum immediately above the surface. But the vibrations are real. When a magnetar's crust cracks in a starquake, the crust rings like a struck bell. The vibration is mechanical, traveling through the solid iron lattice as a seismic wave, not through space. The entire star oscillates at specific frequencies determined by its size, density, and internal structure. These oscillations are called quasi-periodic oscillations, and they show up in the X-ray data following major starquakes. After the initial burst, the X-ray emission does not decline smoothly. It oscillates, rising and falling at specific frequencies that repeat for seconds or minutes before damping away. The frequencies carry information. Just as the note a bell rings depends on its size and composition, the frequencies a magnetar rings at after a starquake depend on the star's internal structure. Different equations of state predict different oscillation frequencies. Measuring those frequencies and matching them to theoretical models gives scientists another path into the interior. This field is called neutron star asteroseismology, borrowing the name from the study of stellar oscillations in normal stars, which in turn borrowed it from Earth-based seismology. The logic is the same at every scale. Make the object ring, measure the note, work backward to the structure. The oscillation data from magnetar bursts has already constrained some models. The frequencies observed in the 2004 giant burst from the magnetar 50,000 light-years away matched predictions for a neutron star with certain interior properties, favoring some equations of state over others. Future instruments with better time resolution would allow measurement of higher frequency oscillation modes, each one carrying additional structural information. A sufficiently precise measurement of the full spectrum of oscillation frequencies from a single burst would effectively give scientists an acoustic image of the interior of a magnetar, an image built from the echoes of a cracking crust, arriving after 50,000 years of travel. The ringing also reveals something about the coupling between the crust and the interior. Different oscillation modes damp at different rates, some quickly, some slowly. The damping rate depends on how energy transfers from the vibrating crust into the superfluid interior. A weakly coupled interior damps the oscillations slowly. A strongly coupled one absorbs the energy quickly. The observed damping rates suggest the coupling is significant, meaning that the superfluid interior actively participates in the dynamics of a starquake, rather than sitting passively while the crust rings above it. The entire star is involved, and the entire star's ringing, decoded from the X-ray light curves that arrive at Earth telescopes, is one of the richest sources of information about the interior that scientists currently have. The star cannot be heard, but it can be read. Two neutron stars colliding is one of the most violent events the universe produces. The merger of two ordinary neutron stars was directly observed for the first time in 2017. Gravitational wave detectors on Earth caught the signal as the two stars spiraled together and merged over about 100 seconds. Light-based telescopes then observed the resulting explosion across the electromagnetic spectrum, from radio waves to gamma rays. The event was called a kilonova and it settled one of the longest-standing questions in astrophysics. Scientists had suspected for decades that the collision of neutron stars might be responsible for producing many of the heaviest elements in the universe. Gold, platinum, lead, uranium, elements too heavy to be made inside stars through ordinary fusion. The kilonova observations confirmed it. The explosion produced an enormous quantity of these heavy elements scattered into the surrounding space. Every gold atom on Earth was forged in an event like that. Now imagine both stars are magnetars. A magnetar-magnetar merger has never been directly observed. Magnetars are rarer than ordinary neutron stars, and two of them, orbiting each other closely enough to eventually merge, would be extraordinarily uncommon. But the theoretical picture of what such a merger would produce is extraordinary. The combined object during the final seconds of inspiral would host two of the strongest magnetic fields in the universe, approaching each other at significant fractions of the speed of light. The interaction between those fields before the stars even touch would produce electromagnetic effects of enormous power. The fields would reconnect and release energy in a process analogous to solar flares, but at incomparably greater intensity. When the stars finally touched, the combined magnetic field of the merged object could briefly reach strengths beyond anything a single magnetar produces, an object with a magnetic field amplified by the collision process itself. The merged remnant would either collapse immediately into a black hole if the combined mass exceeded the stability limit, or form a hypermassive neutron star spinning at extreme rates, radiating gravitational waves and electromagnetic energy across the spectrum at rates that would be detectable across cosmological distances. The heavy element production in a magnetar merger would likely exceed that of an ordinary neutron star merger, because the more energetic and more turbulent conditions inside the merged object would drive heavier nuclear processes. Some scientists have proposed that the most extreme kilonova events observed at cosmological distances, events significantly more luminous than expected from ordinary neutron star mergers, might involve magnetars. The extra energy injected by the magnetic field decay of a newly formed magnetar remnant could power a more luminous and longer-lasting explosion. The connection between the most magnetic objects in the universe and the origin of the heaviest elements on Earth and throughout the cosmos is one of the most striking conclusions that magnetar research has produced. The gold in a ring, the platinum in a catalyst, the uranium that powered early nuclear reactors, all of it traces back to collisions like the one a magnetar merger would produce. A collision of the most extreme objects, made of matter, combining their substance in an instant of almost incomprehensible violence. The universe seems designed, if that word is used loosely, to produce complexity from simplicity. Simple hydrogen formed first, then gravity compressed it into stars. Stars fused it into heavier elements. Those elements were scattered by supernovae and neutron star mergers, and eventually the scattered material formed planets, oceans, and living things. Magnetars sit inside this story. The supernova that produces a magnetar scatters enormous quantities of heavy elements into the surrounding space. The shockwave from that supernova compresses nearby gas clouds, potentially triggering the collapse of those clouds into new stars, some of which will have planets, some of which may eventually develop life. The gamma-ray bursts from magnetar starquakes carry enough energy to affect the chemistry of any planetary atmosphere they reach. At close range, within a few thousand light-years, a major burst could strip ozone layers from Earth-like planets, flooding the surface with ultraviolet radiation. The resulting biological stress could drive extinctions, or it could drive the rapid evolution of resistant organisms, forcing biology to adapt in new directions. The relationship between magnetar bursts and mass extinctions on Earth has been studied, and is considered possible but unconfirmed for any specific event in the fossil record. The nearest confirmed magnetar is far enough away that its historical bursts would not have been lethal to Earth. But over billions of years, a closer magnetar event may have influenced Earth's biological history in ways that are now undetectable. The heavy elements forged in neutron star and magnetar mergers are essential to life. Iron, which carries oxygen in blood, was produced in stars but also in neutron star mergers. Iodine, essential to thyroid function in vertebrates, is a heavy element whose primary production site is neutron star collisions. Zinc, used by hundreds of enzymes in every living cell, has a significant contribution from these events. Life is built partly from the wreckage of the most violent collisions in the universe. There is also a more speculative direction. Some researchers have asked whether the magnetic fields of a magnetar, at safe distances, could play a role in orienting or protecting nearby structures. At distances of many light years, the field drops below any biologically significant threshold. But the question of whether strong magnetic fields in a young galaxy, during an era when magnetars were more common because more massive stars were forming, played any role in shaping the chemistry of early planetary systems, is an open one. The universe's history is a story of extreme objects producing the conditions for less extreme objects to exist. Black holes at galactic centers regulate star formation. Supernovae distribute the elements needed for rocky planets. Magnetars contribute energy, elements, and shockwaves that push the cosmic chemistry forward. Understanding magnetars is understanding a piece of how the universe built the conditions for complexity, for chemistry, for biology, for the kind of organized matter that eventually asks questions about where it came from. The most magnetic thing in the universe is not separate from the story of life. It is part of the same chain that produced it. We have traveled from the surface to the core of the most magnetic object in the universe. We have watched atoms become needles. We have seen empty space split light. We have felt the shock of a starquake that crossed the galaxy and disturbed the air around our own planet. And after all of that, the deepest question the magnetar raises is still open. What happens to matter when you compress it past the point where our physics can follow? A magnetar takes us to the edge. Inside the crust, known physics holds. Inside the outer core, known physics mostly holds. Inside the inner core, theory suggests quark matter, but no observation has confirmed it directly. And at the very center, the models produce uncertainty and competing predictions that current instruments cannot resolve. This is where the magnetar's story meets a bigger story. Physics has a boundary condition problem. General relativity, the theory of gravity that describes black holes and the large-scale structure of the universe, breaks down at singularities. It produces infinite values and then stops. Quantum mechanics, the theory that describes the smallest scales of matter and energy, cannot currently be reconciled with general relativity. Combining them into a single coherent framework is the central unsolved problem of theoretical physics. The center of a black hole, where densities are infinite, is the most obvious place where both theories break down simultaneously, but no information escapes from inside a black hole. The singularity is permanently hidden behind an event horizon. Whatever happens, there cannot be observed. A magnetar core is not a singularity. Information escapes. X-rays leave the surface. Gravitational waves pass through during mergers. Radio pulses pass through the magnetosphere. The interior is not directly visible, but it is indirectly legible, encoded in the signals that escape. If the center of a magnetar contains quark matter, and if future instruments are sensitive enough to identify its signature in the observable properties of the star, that would be the deepest confirmation of matter's behavior under extreme compression ever achieved. It would constrain the equation of state in a way that connects directly to the Big Bang conditions and to the question of what quantum gravity must look like to be consistent with nature. And if the observations reveal something unexpected, something that does not match any current model, that anomaly would be a signal, a hint that the physics inside a magnetar is pointing towards something beyond what we currently understand. The history of science suggests that the most productive discoveries are the ones that do not fit. The anomaly that does not match the prediction is always more valuable than the confirmation, because it shows you exactly where the map ends and the territory continues. A magnetar is the closest thing the universe offers to a safe, persistent, observable test of matter at its most extreme. It has already produced multiple confirmations of known physics, in conditions never previously tested. It has constrained models that will influence physics for decades, and somewhere in the data still being collected, in the burst spectra and the oscillation frequencies and the gravitational wave templates from neutron star mergers, the answer to the quark matter question, and maybe something more unexpected, may already be waiting. The Magnetar keeps ringing. We are still learning how to listen.